Okay, today we are going to continue on our revision. So we are starting with capacity analysis and level of service. In this chapter, we discussed the capacity concept, the concept of capacity, the level of service, and an application for capacity concepts and level of service to determine the level of service for multi-lane highway. So, first of all, to have a background. This is a background about the development of the Highway Capacity Manual, which started in the 1950s and started evolving until the most recent edition is the HCM 2010. However, we are using the fourth edition because it's the available metric version of the Highway Capacity Manual. What are the primary objectives for the Highway Capacity Manual? Was basically to provide uniform guidelines for the nations. Here we are referring to the US, that was rapidly growing highway construction program. That's basically post-World War II. In the 1950, after World War II, there was a construction boom for highways, and so they had to have a uniform guidelines for how to build these highways and how to design it. Also, to assure efficiency and equity and efficiency among transportation infrastructure users in the states. As you know, the United States is a group of states that are united in a federal union, and they must, make sure that there's equity and efficiency for all users of the transportation infrastructure among the different states. So those were basically the initial objectives or the primary objectives for the Highway Capacity Manual. So, what is the definition of the capacity in general? Okay, capacity according to the Highway Capacity Manual is defined as the capacity of a facility is the maximum hourly flow rate. So that's the first concept at which persons or vehicles. So we can measure capacity in terms of persons or vehicles. Reasonably can be expected to traverse a point or a uniform section. So that's the second concept. So the first one, it's a maximum hourly rate. Second, can be measured in persons or vehicle. Third, at a point or a uniform section of a lane or roadway during a given time period under prevailing roadway traffic and control conditions. Yeah, and if we are measuring the level of service at an intersection, so that's under the current signal timing, for example. And there is another concept which is reasonably can be expected. That means repeatability. It's repeatable. It's not one shot. Okay, so these are the five concepts embedded in the definition of the Highway Capacity Manual for capacity. And this applies for different facilities. For example, a runway at an airport, there's a capacity for that runway. An airport terminal, there is a capacity. A bus station, there is a capacity. Bus route, there is a capacity. So all transportation facilities, you can define capacity according to this definition. Any questions so far? Okay. Here we are, discussing each of these concepts. Maximum hourly rate can be measured and expressed in persons or vehicles. Here, prevailing roadway traffic and control conditions, and here the point of uniform at a point or uniform section, and here reasonably expected. So these are the five concepts included in the definition of the Highway Capacity Manual. However, there was another concept that was developed, which is basically the level of service, because the capacity by itself is not an easy to understand or to comprehend by non-specialists in the field. So they developed what we call level of service. It's a grading system from A to F, where, as we know, that A is good and F is failing. So this terminology is easy for non-engineers to understand, and for decision makers to make decisions, and for general public also. So what is the definition of level of service? Level of service is basically a quality measure. It's a measure that we use to describe the quality of operations. Okay, so we cannot say that the highway is congested. What do you mean with congested? That's a very vague word. Okay, or the traffic is bad. You cannot say that. We can say that okay, the level of service for this intersection is either A or B or C or D or F or E. You see my point? So there's a grading system for performance of facilities. Okay, so it's basically a quality measure describing operational conditions within a traffic stream, generally in terms of such service measure. Sorry. Pay attention to this. Generally, in terms of such service measures. Okay, so it depends on what type of service we are talking about. Maybe speed is the service measure, or travel time, or freedom to maneuverability, okay, or traffic interruptions, or delay, comfort, convenience. All of these can be used as a measure for the quality. Okay, it depends on what level of service you are measuring and what facility you are measuring. Okay, so to be more specific, here, for example, if we are measuring, for freeways uninterrupted, if we are measuring the level of service for a basic section or a weaving segment or a ramp junction, density, okay, density basically defines the freedom of maneuverability. Okay, for multi-lane highway, it's also density. However, for two-lane highway, that means it's only two lanes and one direction this way and the other direction this way. That's the two-lane highway. So here the situation is different. We cannot use density as a measure of effectiveness. Okay, so we use travel time. We use the percentage of time spent following another vehicle. That means especially if there's trucks on this road. Okay, so the percentage of time, okay, a driver spent following another vehicle, he cannot pass it because there's another, there's no gap in the opposing traffic. So these are the measures in this case. For interrupted flow, signalized intersection. For signalized intersection, it's delay that determines the level of service. For unsignalized intersection, that means intersection is controlled with a stop sign. Also, again, the waiting time or the delay. For urban street, the average travel speed. Okay. For mass transit, we mean buses and stuff like that. So the service frequency, how frequent the buses are in per day, or the service headway, the time between two successive buses, and the percentage of passengers to seats. Okay, so all of these three are used to describe the level of service for buses. Spaces, for pedestrians, we measure the level of service based on foot square per pedestrian. For bicycles, frequency of conflicting events. Okay, so these are examples for the measure of effectiveness that we use to measure the level of service for different facilities. However, there are some critical issues with this concept of level of service, which is basically that it's a grading system. It's a step function. It's A, then we go to B, we go to C, we go to D, then we go to E. As you can see here, it's a step function. So S1 here, S2, we have these three states. In reality, the difference between S2 and S3, okay, is very small. But S2 is in class B, S3 in class C, okay, and S1 also, which is near A, is still in B. So, however, 2 and 3 are almost the same, but they are in two different categories or two different levels. S1 and S2 are totally different, but still they are two. So that's the main disadvantage, because it's a step function. Okay, so we end up with this situation. Okay, there is another issue. Okay, most level of service criteria are based on the collective judgment of professionals exercised through the Highway Capacity and Quality of Service Committee and its subcommittee. That means this level of most of these criteria based on judgment of professionals. Okay, so that's another issue. Any questions so far? The common service measures used in it's basically speed, travel time, and delay. Freedom to maneuver, it's basically traffic density, traffic interruptions, comfort and convenience. These are the primary service measures used to determine the level of service. Here we have also let me just clear these things. There's another concept, which is basically the service flow rate. Service flow rate is the flow rate at the maximum flow rate at specific level of service. Okay, so for a level of service A, there is a maximum flow rate. For B, there is a maximum flow rate, and so on. طيب, هنا we are talking about problems with level of service. Okay, so the key problem, single set of level of service criteria, different levels of perception. That means the density or freedom of maneuverability. Maybe this is, A for one area, maybe it's, or B for one for a group of users, maybe it's different for others. For example, delay. Okay, delay perception is different from one city to another city, from one community to another community, depending on the general acceptance for the public for this level of delay. Okay, for example, here, what might be acceptable delay at an intersection in the MAM city, for example, might not be acceptable at a similar intersection in a small community. You see my point? Some state and local government have, yes, this is not applying for us, but that's basically what applies for us. Okay. That's why we came up with what we call volume to capacity ratio. So we don't rely only on level of service. We have to calculate the volume to capacity ratio, because volume to capacity ratio is a parallel measure. Sometimes, for example, the level of service at signalized intersection is F. That does not mean the problem is in the infrastructure, maybe in the control condition. Okay, the traffic control system that you have, you might, if you improve the traffic control or improve the signal timing for that intersection, we might get a better, level of service. So here we use the V over C ratio as a guideline to see whether we need to as a second judgment. Okay, here we discuss the level of service for multi-lane highway, and we define the level of service A, level of service B, C, D, E, and F. And we discussed that before. And we said that the cross-section, we have cross-section elements, which is basically for multi-lane highway. There's sometimes we have median, sometimes we don't have median. We have the travel way, which are basically the lanes that the traffic use, and there's the shoulders on the other side, and these are also usable shoulders. And here we discuss the standard condition or the base condition for design for multi-lane rural highways is basically that we are assuming the standard condition that we have 3.6 meters lane width, only passenger cars, no direct access points along the roadway, a divided highway, that means we have a median, a free flow speed, okay, higher than 100 kilometers per hour, and we have 3.6 meters minimum total lateral clearance. And we discussed the lateral clearance as basically total lateral clearance equal basically the lateral clearance right plus lateral clearance left, and taking in consideration that each of these should be less than or equal 1.8 meter, or a maximum for each. The maximum is 1.8 meter. That means if you have a shoulder that is 3 meters, we take only 1.8 and we plug it in here. Okay? And we had examples on that. So the first step is basically estimating the free flow speed by determining the basic free flow speed and subtracting these correcting adjustment factors. The first adjustment factor for lane width, for lateral clearance, for median, for access points. And we discussed the charts that you can get these values from. Then we convert the volume into passenger cars equivalent volume by dividing the volume by the peak hour factor and the number of lanes and the adjustment factor for heavy vehicle adjustment factor and the driver population factor. The FHV, it basically converts eliminates the trucks and heavy vehicles and convert it to its equivalent number of passenger cars. The FP, this is an adjustment factor for the driver population, especially if you are in a tourist area and you have drivers that are unfamiliar with the site, so usually they cause sometimes delay in the roads. So these, unless usually use this equal 1 unless we have information regarding this FP. Then we have the VBC here, and we have the free flow speed here. Then we enter, okay, and based on this we say that we have, this is our level of service. In this example is basically D. So we can apply this method in operational cases. Okay, the design input. So that's for operational case that we have an existing facility and we want to determine the level of service. So the objective is basically to determine the level of service. The input is the number of lanes, lane width, median, shoulder, traffic volume. So this is the geometry of the facility or the highway. That's the traffic demand and the topography and the peak hour factor and the heavy vehicle percentile. Then the output will be the level of service. There's also another application which is basically designing and making a new construction. So for new construction, what we have a design volume, we have target level of service, we have right of way, which means the area that we can build our new facility in, and the topography, which is terrain level, rolling level, mountains, and so on. The output would be the number of lane width, median, shoulders. Okay, which is basically the cross section of the road. Given that this dimension should be less than or equal the right of way that we have it as an input here. Okay, and basically we have a target level of service we need to meet in the design. If the design doesn't meet the level of service, then it's a failed design. Then we had this example for new construction, and that was the end of module 1. Any questions so far in module 1? Yes.
Clear, clear.
Next, we started on the highway geometric design. And before we started on the highway geometric design, we discussed the highway functional classification. And we said that in any trip, a trip composed of basically main movements and transition, distribution, collection, access, and termination. That means you start from your home, okay, and you access the network. Then we go to the collection, okay. Then we go to the main movement. Then from the main movement, we go to the transition. Then from the transition, we go to the distribution. Then we go to the termination. That means if you, let me just draw this again. Okay, let me draw another example here. If that's your home, okay, from the streets that you have in front of in your neighborhood, you get access to the highway. So this is highway. Okay, so that's from here, that's access. Then you go to a collector road in your neighborhood, that's the collection. So here we have number 5, here we have number 4 access, here we have number 1. And most of the trip goes on this highway. Then we go to a transition from the highway to another distributor. That's like, for example, exit ramp or something like that. So that's number 2. Then from the distributor, okay, we go to your destination. So that's origin, and that's your destination. And this is number 6. That's the termination. Okay, as you can see, the accessibility for the main movement, we spend it on a highway. Most of the trip, if you measure it as a distance, you will find that most of the trip, okay, 80% is spent here. This is little, and this is significantly less than that. So the main movement, what are the characteristics on the main movement? On freeway or highway, usually. And usually it has a high speed. Also, the access to freeways and highways are limited. You cannot access the freeway or highway from any point. Okay. For the distributor, these are the arterials and collectors. It has moderate speed, and also it has a moderate access. For the access and terminal, these are the local streets or the neighborhood streets. You have low speed, but there is high accessibility. All households are on local streets. So that leads us to this point. This point means that the class of the facility, there is a relationship between mobility and land accessibility. So that's the class. For high class, okay, like arterials and highways and stuff, the mobility is high, but the accessibility is low. This gray area, that's accessibility. As we go below in the rank, okay, the mobility reduced and the accessibility is increasing until we get to the local streets. You see that the mobility, we are referring with mobility with the speed. Okay, the speed, mobility slows down or gets reduced, and the accessibility is starting magnifying. Okay, so here we are saying traffic volume is at its highest at the top of the classification. Also, the traffic volume here is maximum. As we go below, in the lower in the rank, it gets reduced and gets here miniature. Okay, at the top of the classification, mobility is very high and the access is limited. At the lowest in the classification, access is very high and mobility is very low, and also the volume is very low. Okay, design, control, and criteria. before we start to designing a highway, we need to understand what are the control criteria for the design. So for the design criteria for a highway facility, we have first of all the projection of future traffic demand. So basically depends on the facility. Okay, so if we are talking about, just the right of way for a highway, okay, we plan for the life expectancy of 100 years. Okay, but it's not necessarily that we build right away on this right of way. We might build on a reduced, but we have an expansion up to our projected for 100 years, for 100 years to come. For my minor drainage and base course, so that's the base course of the highway. We plan for 50 years. Why? Because the base course and the drainage is difficult to replace or expand after constructing the highway. Bridges, it ranges from minimum 25 years to 100 years, because this facility we don't build every 10 years or so. Pavement resurfacing every 10 years, okay, and maybe less than that. Pavement structure, it's a new pavement structure we plan for maybe 20 to 30 years old. Okay, so basically, look this way. We might get the right of way for 100 years, but when it comes to the pavement structure, we constructed for the projection of 20 to 30 years to come. Pavement reconstruction, 5 to 10 years. Any questions so far? Okay, so that was the projected, the first criteria was the projection of future traffic demand, or the planning year, if we say it this way. The other criteria, which is basically speed. Speed basically is a key design control for highway geometric design. As we discussed in the horizontal curve design, the design speed, the speed on the highway, that was a critical design factor. Why? Because from the speed we determine the stopping side distance, which governs most of the elements in designing horizontal curves and vertical curves, or the horizontal alignment and vertical alignment. Okay, as we mentioned, it defines key design elements in highways such as horizontal and vertical curves. It plays a key role in determining lane capacity and highway facility in general. Speed is a key factor in functional classification of a highway. We have types of speed. What are the types of speed? We have two types of speed: operating speed and design speed. Operating speed, that's the speed expected, that 85% of the observed spot speed. Okay, so that's the observed speed of for the road users. The design speed, these are selected speed. So there is a fundamental difference between operating speed and design speed. What is this fundamental difference? This is an observed operating speed, and it comes from the spot speed study, so that the 85th percentile of observed spot speed study sample, okay, that's the operating speed. Tamam? But for the design speed, this is a selected speed value. Okay, how do we select the design speed? It must be, first of all, logical with respect to topography, adjacent land use, anticipated operating speed, functional classification of the highway. The design speed should be selected as high as possible. That's first. That's one critical issue. However, we should give consideration for the desired degree of safety, mobility, and efficiency. These three factors, okay, must be taken into consideration. Any questions so far? The recommended design speed for rural highways, 120 kilometers per hour. For suburban freeways, 100 kilometers per hour. For suburban elevated and depressed freeways 80 to 110, for urban arterials and streets from 50 to 100 kilometers per hour. The third criteria, which is basically the level of service, target level of service, design level of service. So for freeways, rural level, it's P, rural rolling B. For rural mountainous, it's C. For urban, suburban C. So as you can see, for urban, suburban, it's C, C, D, D. That's for freeway, arterial. For collector and local streets, it's D, D. Okay? For the rural mountainous, it's C, C, D, D. For rural rolling, okay, يعني أرض في الضواحي وهضبية, it's B, B, C, D. For rural level, B, B, C, D. As you can see, some of you might be wondering why we design the highway for example, a B, or freeway in urban and suburban areas to be at level of service C. The answer is this. We are designing this for the peak hour, okay, at the planning year. At the planning year, which might be 25 years later. Okay? So we started with the highway horizontal alignment, and we started talking about the horizontal alignment. The horizontal alignment, we said that the horizontal alignment comprised of a group of tangents, okay, connected together by horizontal curves and vertical curves. So we started with the horizontal curves, and the horizontal curves, as you can see, they have different types. There is a simple curve, and this is basically what we would like always to construct. There is a compound curve. The compound curve, it starts with a radius for a segment, then another radius for the other segment. And this is we don't really like. However, sometimes we are forced to do it, especially if we have a mountain or something like that. And as well is the reversed curve. The reversed curve we try to at all measures to avoid. How can we avoid this? Is basically to have a curve, then a straight segment, then another curve. Okay? We try to have this straight segment. Why? As you studied as we discussed in the horizontal curve, we have super elevation. So as you can see here, we will have super elevation. If we take a cross section here and cross section here, so the super elevation will be like this at section A. That will be the profile. Okay, at section B, the super elevation will be like this. So, flipping the cross section from at a single point here, that's very problematic. So we prefer to have a straight segment to level and make this transition smooth between the two super elevations, because we have two opposing super elevation at one point. Here are the geometric elements of the horizontal curve and the layout. Okay, we mentioned that we have we have discussed this before. We're not going to elaborate more on this. Or do you need me to elaborate on this? شباب? Okay. So there's another issue, which is basically the degree of curvature, and the degree of curvature is basically the angle corresponds to an arc length of 30 meters. So that's a measure for the severity of the curvature of the horizontal curve. And that was the equation that we used for the design of the horizontal curve, which is v square over gr. G, that's the gravitational acceleration, and r, that's the radius of the curve. E, that's the super elevation value, and FL, that's the side friction, or the side friction. Here we have this derivation for this formula, and we eliminated here, one of your colleagues asked me why we eliminated this product. And basically, if we go through this equation, this part is eliminated because we have two small values. For example, the lateral friction, it's around 0.15 to 0.1, and the super elevation is basically E. It's the maximum is 0.08, for example. If you multiply these two values together, we end up with a very small value that we can omit and simplify the equation. If we don't do that, then we need to take this and write here 1 plus E 0.01 E multiply FL. Okay, as I mentioned, this value is extremely small that we can omit and neglect. Any questions so far? Okay, here we are having the maximum super elevation, and the maximum super elevation is between 4 and 12%. That's the AASHTO standards. But in reality, most contractors, they prefer to have it at 8 or lower. The typical is 5%. And the side friction we can determine from this curve. And we are going to stop here, and we are going to continue next lecture, inshallah. Any questions so far?